Well, now we get to the idea of this three-dimensional space version of Theorem 15.1 involves something called the curl of a vector field. So what is the curl of a vector field? The curl of a vector field f of x, y, z is m times I plus n times j plus p times k. Notice that the curl is a vector and is defined by curl of f equals del cross with f of x, y, z. Now what does that mean? It happens to mean something involving partial derivatives of our m, n, and p times I plus partial derivatives times j plus some partial derivatives times k. So, and by the way, if it happens to be the zero vector, like if this is 0, this is 0, and this is 0, then we say the vector field f is irrotational. And it kind of means what it sounds like. That means this vector field is not rotating in any way, shape, or form. So this notation and definition comes from viewing the gradient as a result of a differential operator del acting on the function f. And so this determinant, you know, this is not a good way to memorize this. The best way to memorize curl of f is find the determinant I, j, k in the top row. This, I know, is not really good form, but it works as a memory device. Partial of something with respect to x, partial of something with respect to y, partial of something with respect to z, and m, n, and p, and that's this m, n, and p in the last row. Now, I'll demonstrate that for you here to show you that it's the same, right? If we were to look at this, it's going to be I times its minor partial with respect to y of p minus the partial of z with respect to n. Sorry, I didn't say that right. Partial of n with respect to z, that's better. See, partial I times partial of p with respect to y minus partial of n with respect to z. Look, that's it. Times I. And then plus minus, so minus is coming into play, j times its minor, which is partial of p with respect to x, minus partial of m with respect to z. See, there it is. Times j. And then plus k times partial of n with respect to x minus partial of m with respect to y. And there it is. So this is the easy way to think of curl of f. A nice memory device is just evaluate this determinant. Even though it doesn't make sense to say, why this times this? No, it's this of this. And if you can tolerate that, then we got an easy way to pick up the curl. So, find the curl f of the vector field and evaluate at the point 2, -1, 3. So our f of x, y, our vector field is x squared z times I minus 2xz times j plus yz times k. So the curl of f, well, again, this is our memory device. Actually, when I made this, I just copied it and pasted it and changed the last line. This is the m, x squared z. This is the n, 2xz, minus 2xz because of this minus sign here. And then this is the n, y times z. So let's see, it's I times partial of this with respect to y, that would be z, times partial of this one with respect to z, which would be -2x. So that should be z minus, z minus a negative, so z plus 2x times I, and then minus j times partial of this with respect to x, and that's 0, and then minus partial of this with respect to z, and that's x squared. So it's minus a negative x squared. So therefore it's plus x squared times j. And then finally for the k, we got partial of this one with respect to x, that's -2z, and then partial of this one with respect to y, and that's 0. So it's just -2z. So there's our curl of f. So the curl of f at the point 2, -1, 3 Well, that would be 3 plus 2 times 2, and that would be 7i. And for our j term, it's just x squared, that's just 2 squared, and that's 4. And for the k term, negative 2z, and z is 3, so that's negative 6k. So this is the curl of f at that particular point. And there's a physical significance for this curl, but it will be later in the chapter.